Hello, everyone, and welcome to another exciting TIES webinar. My name is Kenny Coogan. I am the Center for Inquiry Education Coordinator, and the education programs for Center for Inquiry include TIES, which is the Teacher Institute for Evolutionary Science, and we're hosting this webinar, as well as Generation Skeptics. And then our third branch is Science Saves. And we're excited to have David here for our first 2024 webinar. And we have quite a few other webinars this year. We only have webinars during the school year, September through May. You can go to our website, tieseducation.org, or to our Facebook page to see upcoming events. For the month of February, we have 3 really great webinars all around Darwin Day, which is Darwin's birthday, which is February 12th. And with that, David, you got to make the screen bigger again. It keeps kicking you
out. Okay.
And today we're going to be talking about his book, Predicting Our Climate Future.
Brilliant. Thank you. Yeah, thanks so much for inviting me to give this webinar. I'm very pleased to do so. What your organization does seems absolutely great, but you don't think you have very many talks on climate, so it's very exciting to be giving you a talk on climate. So my book and my talk is really about the essence of climate change. It's what it is and how we can understand it. I think maybe quite often we think about climate change and we think that or we say the science is done, now it's time to act. And I think my perspective here is it's absolutely certainly the time to act. Indeed, it was probably the time to act 20 years ago. We have quite enough knowledge to know that we need to act. But it's not true to say really that the science is done. In fact, the climate change raises many radically new and challenging issues for how we go about science and how we think about the links between science and social science and society. And there's lots of really exciting stuff there. So my book, along with its title, is about what we know, what we don't know, and what we can't know. But it's perhaps principally about what we don't know and what we can't know, because that's where the interesting, challenging issues are. And I guess what I hope to achieve with my book is to sort of instill inquisitiveness in the readers and start asking questions about how we address all the really difficult questions that are raised by climate change. And I try to do that through a range of disciplines. A lot of it is in maths and science, but there's chunks in economics and in policy and social science. That's all there in the book. And to do that, I need to address I need to address uncertainty. I need to address the things that we don't know. And I would argue that those things that we don't know, the uncertainties, are kind of part of what we know. We know about them. They're the type of information that we need to be building into both our science and our policy responses. Now, a number of people are concerned when I talk about this. They're concerned that by highlighting these aspects of uncertainty, that we might undermine efforts to respond to climate change. And in all honesty, that fear is something that I have too. I worry that by talking about the uncertainties, I might be undermining our response to climate change. But I don't think that's true. In my experience, talking about the uncertainties and highlighting what we know confidently within the context of all the sorts of things that we don't know and where we have challenging research still to do, actually engages people. It engages a much wider range of people. It engages people across the political spectrum because it rings true. We don't have certainty in many aspects of our lives, and certainly not many aspects of our social policies. So people don't expect to see certainty in climate change, and presenting it as too certain actually undermines the ability to communicate the need to act. So I think raising the uncertainties, just and highlighting the exciting science, the maths and the economics that needs doing is important for enabling society to respond. So with that introduction, what's coming up in my talk, what I'm going to talk about is somewhat about what we know, which is essentially that we know that human-induced climate change is a real threat to the environment, but also to the societies and cultures in which we live. And then I want to give just a couple of examples of the challenges, the things we don't know and things we can't know, the challenges in math, science and social science that we need to address. There are lots of these in my book, but I'm going to highlight a couple of them. But before I get to that, I want to sort of mention a couple of things about why climate change challenges really the scientific method about how we go about science in so many different disciplines. Climate change raises some challenges to that. And I want to give two reasons for that. The first is extrapolation. Climate change, emissions of greenhouse gases into the atmosphere, is driving the climate system into a state that we have never seen before. And this plot here just shows why that's the case. It shows carbon dioxide concentrations in the atmosphere over the last 650 million years. And over that period, it's been varied quite a lot between ice ages and interglacial periods, but it has never gone below 180 parts per million, and it's never gone above 280 parts per million. In the last 200 years, particularly the last 50 years or so, it has gone up to 418 parts per million. And when you include other greenhouse gases, that's the equivalent to about well over 450 parts per million. These gases trap energy in the atmosphere. They trap energy in the lower atmosphere and keep the planet about 30 degrees warmer than it would otherwise be. And they're changing massively as a result of human activities. That is driving the system into a new state. It's a reason to be concerned about climate change, but it also means that the observations we have for the past don't represent the type of behavior that we will see in the future. And this isn't like an experiment that you can do in the laboratory where you can just repeat it and look at it in different ways. We've only got one 21st century, and we're taking us into a state that we have never seen before. So we don't have observations of the system in the state that we want information about. So that's one thing. The other thing is complexity and nonlinearity. What I mean by this is when we do science, usually we try and isolate a small aspect that we're interested in, the particular thing, and we try and get rid of all the other aspects of the system so that we can just focus on one element. But we can't do that with climate change. We're studying the atmosphere and how it interacts with the oceans, with the ice sheets, with ecosystems, with all sorts of different components. And we're trying to predict, we're trying to understand what the changes will be to the thing as a whole, to everything. And along with that, many elements of the system are what's called non-linear, meaning in this case that we have a sensitivity to the starting conditions. So we have what's called mathematical chaos, and the picture here is just what's called the Lorentz attractor. It's part of mathematical systems which have a high sensitivity to the starting state. I'm not going to say too much more about that, but there's lots of fascinating things there, and climate change taps into those. Okay. So let me move on to what we know. And what we know is really that climate change is reality, that human-induced climate change is reality, and that it poses a serious threat to societies. And I'd like to just take you through the sort of basics of why I believe that's the case, the basic science. So as a starting point, one thing we know is that everything radiates energy in the form of light or electromagnetic radiation. And what type of radiation depends on the temperature of the thing that we're interested in. So if you look over on the right here, we have a red curve or an orange curve there. It's which shows the distribution of types of light emitted by the sun. And that's what's known as shortwave radiation. On the right-hand side, we have the distribution of different types of radiation, all in the infrared band that is called long-wave radiation, and it represents the types of radiation that are emitted at temperatures typical of the Earth. And crucially, what you see there is the shortwave radiation from the sun is completely separated from the long-wave radiation from objects on Earth. So this is sort of basic physics. It's sort of high school level, undergraduate level physics. We know this. We also know about the greenhouse effect, which comes about because of how carbon dioxide and other greenhouse gases interact with these different forms of radiation. What we know, you can study this in the laboratory, is that carbon dioxide and other greenhouse gases absorb long-wave radiation, but they let short-wave radiation pass straight through. So what that means is that the light coming from the sun comes straight through the atmosphere and down to the surface of the planet. Some of it is reflected by ice sheets and by clouds, but the rest comes straight through the atmosphere down to the surface of the planet. However, the radiation, the light emitted by the surface of the planet, the radiation emitted by the surface of the planet, can't get out. It can't get out because of the greenhouse gases in the atmosphere. So it's absorbed in the atmosphere and then re-radiated. And then some of that makes it out to space, but some of it comes back down to the surface of the planet. And the greenhouse effect, we know, keeps the surface of the planet about 30 degrees warmer than it would otherwise be. It makes the planet hospitable. Now, we know that also the carbon dioxide is a significant fraction of this greenhouse effect. It's about 20%. So if we got increasing carbon dioxide, we would expect the surface of the planet to warm. Now, we also know that carbon dioxide concentrations in the atmosphere are increasing. We simply have measurements of that. The longest direct measurements come from Mauna Loa in Hawaii, and we have this curve here. It's quite a famous curve called the Keeling curve, which is just direct observations of carbon dioxide in the atmosphere since the 1950s. And we can see that they're steadily increasing. And we can match that up with the emissions that we have from human activities. So we know that this increase is due to human activities. Okay. However, when you start putting energy into something, it takes time for that thing to warm up. This is true in something as simple as a kettle. When you switch on a kettle, you don't simply have boiling water ready for making a cup of coffee. It takes time. You've got to wait for it to warm up. It's the same with the planet. When you increase carbon dioxide in the atmosphere, you're trapping more energy. You have energy going into the lower atmosphere and into the ocean, but it takes time to warm up. There's a delay in the system, particularly because of the water in the oceans. We also know that energy flows from the deep oceans to the subsurface oceans to the atmosphere. It flows back and forth over different periods of time. And because of that, there's a lot of variability in even the surface temperature of the planet. So we get warming, which is what you see on this figure on the left, the increasing temperatures, global temperatures, but it's not neatly matched to the increasing carbon dioxide in the atmosphere. There's a delay and there's a lot of variability. All of these things are things we know. We also know, I seem to have jumped too far. Oh my goodness. Let me go back. We also know from social science, from common sense really, that we're not going to stop emitting greenhouse gases overnight. So the warming is definitely going to continue and going to continue getting more extreme. Where that leads us is to say, well, okay, it's going to continue warming, but the big question then is, what will that warming and the climate changes associated with it, what will that lead to in terms of changes to our society? That's where it starts to get a little bit more difficult to say quite what climate change will mean. Um, there are a lot of things we can say about it, though. Things that we can say that we know. We know that it will lead to changes. It will lead to regional warming. We know some aspects of those regional warming. We know that it will lead to changing water availability and changing flood risks. We know it will lead to changing agricultural production and the potential to produce agriculture, and hence changes in industries like tourism and where we want to go on holiday, where it becomes too hot. If we think about ski resorts may not be able to provide the facilities, might not be able to provide the snow that we want. So we know that it will have an impact on our societies. So it means essentially change. It means that we will, in the future, be living in a world where we are more vulnerable to hazards, whether that's heat waves, flood risks, wildfires. And that is typically how we tend to talk about climate change. But it's more than that. It's not. I think it's very easy for many of us in society, particularly in Western nations, to think, well, okay, there'll be more floods, there'll be more heat waves, but we can put in extra air conditioning and floods. Surely we can build more flood defenses. Basically, we've got concrete. We can surely channel where our water goes. We can surely manage those flood risks. I'm not sure that's entirely true, but we will certainly be trying to do that. But it misses the point of how our societies work. I work in the London School of Economics. I'm a physicist, but I work in the London School of Economics. And the reason I do that is because the changing understanding, the changing climate resides in the realm of physical sciences, but the consequences for society sit in the realm of policy and economics. And how we connect these is desperately important. And the way I see climate change is we will face these increasing hazards over time, but that has a consequence for how our societies work. Even if we can protect ourselves from individual hazards, we will be facing these hazards more and more frequently. And that means we will continually need to spend on maintaining our infrastructure, on rebuilding our infrastructure, and the facilities that we take for granted. And that means that we look to our governments, to our communities, to help us recover from these constantly increasing environmental risks. And that means a drain on our society. It means we will have less money to spend on education, on the arts, on sport, on building a more equal society, on providing care for the vulnerable in society, for our elderly and the like. It means a constant drain on our society, which means we can't make our society better. It means we're struggling to keep our society providing the facilities that we currently have, and probably a degradation on what we can do and what we can provide. So climate change is a drain on our potential to invest in the things that we want. That's its core element, and we need to in academia we need to provide pictures of quite what that means, of teasing apart what that means for the world that we're going to live in the future. Okay, so those are those are things that we know. We know about the serious of the threat. We know about the physical side, and we know that will lead to a degradation in the societies that we're living in the future. And in my book, I go through these in terms of things that are known beyond reasonable doubt and things that we can confidently expect and why we know that. So all these things are known. We know that they're important, and we know we need to tackle climate change. But what about what we don't know and what we can't know? So let me address first what we can't know. So to address some of the things that we can't know, we need to think about what climate is. And for me, the best definition of climate, the definitions in the American Meteorological Society and the definitions in the Intergovernmental Panel on Climate Change reports. But for me, the best definition comes from a book by Robert Heinlein called Time Enough for Love, where he put in a definition which was climate is what you expect, weather is what you get. And I like this definition because it's simple and it can apply to maths and it can apply to physical sciences. It makes climate relatable and it's simply accurate. If you think about the weather that you're going to experience wherever you are tomorrow or next week or maybe on the 12th of July, will be what it is. The weather is just what it is. It's hot or it's cool or it's rainy or whatever it might be. But if we're looking ahead, perhaps to July, we have some knowledge of what to expect. We have some different types of weather that might occur, but we also have probabilities for what types of weather will occur. And those probabilities for different behavior represent what we expect for weather in the future. So this is really very much like the roll of a dice. If you look at the green dice here, the green dice on the picture here is a standard six-sided dice. And when you roll a dice, you don't know, you can't know what the outcome of the dice though is going to be, but you do know really well, probably, what the probability distribution will be. You know you're going to get a number from 1 to 6. You know you expect, if it is a fair dice, that each of those numbers is equally likely. So you have what's called a probability distribution for the different outcomes of the throw of a dice. And it looks like this line on the right is known as a top hat distribution, hence the little stick man with a top hat on. That gives the probability distribution. And the climate of the dice is the probability distribution. The weather of the dice is what particular outcome you get with any particular throw. Okay, so climate is an equivalent to that. Climate change is a change in that distribution. It's saying we have some distributions for what weather can be, and they're going to change. And we can think about that in terms of dice as well, or at least you can if you're me, because I'm a slightly weird person who's gone away and made a whole load of strange dice. So the blue dice here, as it turns out, is a fair dice. Each side has a 1 in 6 chance of occurring, but there's no 3 on it, but there is an 8 on it. So the probability distribution looks like this blue line on the right. The black dice also is strange in that it has a 7, but it has a 7 rather than a 6. But in this case, it's a loaded dice. It's a weighted dice. So the 4 comes up much more likely, is much more likely than any of the other numbers. But the other numbers are possible, but of course a 6 is no longer possible. So if you imagine climate change is like changing from the green dice, it's what we're familiar with, to some other sort of dice which might have different numbers on it and might be loaded in a different way. The probability distribution is changing. With climate change, we can get an idea of what those changing distributions are using climate models. And what I'm showing on the right here is a changing probability distribution. So the reds are most likely, the yellows are least likely, well, and white is not, doesn't occur at all. And what we have here is the June, July, August average temperature of the Amazon basin from a climate model. With steadily increasing carbon dioxide concentrations. So this isn't the 21st century. It's about a 1% increase in carbon dioxide concentrations over a period of time. And we see that the distribution that shows this steady warming, but we still have this distribution. We always have a distribution. The black line here shows the median. So the average of this distribution, and it steadily increases. But if we take just, and how do we get that? We get that distribution by taking a climate model and running it lots of times. And each simulation with the climate model, uses a very slightly different starting condition. I mean, I'm talking about changing the temperature over Hawaii, for instance, by a hundredth of a degree at the starting point, and then running it forward over 100 years. And from those multiple simulations of the future, we can build up those probability distributions. But it's important to remember that in reality, we'll only experience one future. And this blue dashed line here is an example of what one simulation of the future would be. So when we predict future climate, we get a change in probability distribution going into the future, but the particular trajectory that we will experience will not look like that probability distribution. It certainly won't be the median of that line. It will be a trajectory which can deviate from that line quite substantially. And what we see in this blue line is most of the time it wiggles around close to the median. But for 10 years, 10 years, at this point, sort of 30, 40 years in, this particular trajectory experienced a much greater warming. So at the start of the simulations, we're looking at temperature in this season and in this place of about 24 degrees. And over time, it goes up to about 30 degrees towards the end of the century. But even in this early period, we might suddenly get a period where we're up to 30 or 31 degrees for a period of time. That's something we can't know. That's what we can't know. That's the chaotic variability. It's the result of the butterfly effect. But we can know that the distribution is warming. Okay. Now, how long have I got? I think I've got another 5 or 10 minutes. So I will go into what I find really interesting, what we get into, what we don't know but possibly can know, questions of how we understand climate prediction. One of the things we simply don't know, we haven't really asked the questions yet, is how close to representing the real world does a model have to be able to predict these changing distributions with confidence? And this is a question which touches on physics, on maths, but also on philosophy. So let me just talk about this plot on the right here. This plot represents a mathematical system, a chaotic mathematical system. So it's a system that is subject to the butterfly effect. And it represents an ecological system. So what it does on the right, on the x-axis, you've got something that represents the population of something in a particular season. So that might be rabbits, or it might be fish in a pond, something like that, from 0 to its maximum. And on the y-axis, it shows you the population that you will see in the next season. It's a particular system called the logistic map. And what you see is if you've got a low population this season, then it goes up. Next season, it's going to be higher. And then the following season will be higher still. That's kind of saying if you populations in ecological populations of species like rabbits or fish in a pond grow. If you've got small numbers, it will grow. But if you've got very high numbers, they're using the resources available to them to their maximum. There aren't basically that. It turns out there isn't enough food to keep all that population alive. So if you've got a very high population, then the next season it falls down to a very low population. Okay, I'm using this just as an example of a predictive system that has non-linearity in it. So it's similar to a climate model in that way. And I've got two of them here. I've got two models essentially, but one of them I'm going to call reality. So our model is going to be a simple representation. Reality is the same as our model, but with a slight extra perturbation, a slight extra adjustment. And if you look at these two lines, they look very close to each other. It's impossible to tell the model from reality. So it looks like we've got a very good model. What happens, though, if we say, well, we've got some observations of our population this season, but we don't know it exactly. So we need to take a number of different starting populations, and we're going to run them all forward. So we have a distribution to start with, and we're going to see how that distribution changes over time. I'm really pushing you on to the edges of our understanding, to the edges of research here. But if you imagine we have that distribution to start with, and we take it one season forward, our model and reality predict the same thing. Two seasons forward, they do the same thing. Three, they're pretty close. Four, they're pretty close. Five, they're pretty close. Starting to separate after six. But after 7 seasons, suddenly our model and reality are predicting different distributions, different probabilities of populations in this system. And after 10 seasons, we see entirely different results. Now, this, I'm talking about ecological systems here, but this is saying really that any nonlinear system of which climate models are a sort could produce the wrong probability distributions after some point in time. Now, I find this just really exciting. This is raising questions of how close to reality do we need our models to be in order to be able to trust them to provide the probability distributions for the future. Now, bear in mind, that sounds very skeptical. It seems as though I'm saying, look, you can't trust climate models. But actually, remember what I was saying about what we know? We can trust climate models for some aspects. It's only some aspects of the details of climate predictions where we enter into the consequences of these nonlinearities. So we need to separate what we know from what we don't know, but we also need to ask questions like, how do we use our models? What aspects of our models are reliable and what are not? And this is kind of the cutting edge of climate science at the moment. Right, I think I've only got about 5 minutes left, so I'm going to jump over. Well, no, I will say a few words about this. Climate models are fantastic tools, but the question is how to use them. What we see on the right-hand side here is multiple different climate models and their projections. Well, actually, they're simulations of the past, simulations from 1860 to 2010 or so, in Central North America. And we see that they're all representing different temperatures over Central North America. And that means essentially that they can't be realistic. They're going to represent where the snow line is, where trees are, where ecosystems are differently, or maybe they're going to represent them the same, but that means that their representation of trees and how they respond, and snow and how they respond to temperature isn't going to reflect reality. So there's a sort of element in which they're not realistic there. But on the other hand, if you look at the top left here, all of these models predict increasing global average temperature. So we have this balance between confidence and uncertainty. We can be really confident that global mean temperatures are going to increase. In fact, we can be really confident that regional temperatures are going to increase. And in fact, we have a lot more knowledge than that. At the same time, if you're wanting to say, what does that mean for where you live? What does that mean for the particular systems, particular ecosystems and weather systems that are important where you live? Well, the differences between the models really matter then. So painting that detailed picture is probably something we can't do. But the fact that so many different models, so many that are really quite different, all show global warming, leads us to confidence, extra confidence that climate change is a reality and something that is important. Okay, a couple of final slides. I've talked a lot about the physical side of climate change and the math side of climate change, but there are other things that we don't know that we need to ask ourselves questions about. One is very much in the economics of climate change, which is how much damage will climate change cause to our societies? This is something that we can think about and we need to paint better pictures of. What I'm showing on the right here are two what's called climate change damage functions. They show how much our economies will lose, the decrease in welfare, or to think of it in economic terms, the decrease in gross domestic product, the welfare of our societies, with increasing global average temperature. So if our global average temperature increases by 10 degrees, Some economists have said, well, maybe that will lead to an 18% loss in welfare for our societies. Other economists have said, well, that might lead to a 98% loss to our societies. We don't really know how to quantify these the consequences for our society. There's lots of work being done, lots of really interesting work being done. But as you can see from the difference between these two curves, economists come up with very different answers here. Most physical scientists that I know think that this lower line is ridiculously low. When you go to a room of physical scientists and say that with a 10-degree warming, you would only have an 18% loss of economic output, they think that I am teasing them, that economists clearly wouldn't think this. It seems ridiculous. 10 degrees is massively more than the change between an ice age and a non-ice age. No physical scientists that I know think that that's reasonable. But some economists think it's reasonable. More importantly for me is that these two curves seem to show only a few percentage points loss in global economic output at 2 degrees warming. And of course, 2 degrees is what we're trying to get agreements to achieve, to limit it to 2 degrees. So is maybe only a percent or two a small impact? Well, when I talk to my economist colleagues, they throw up their hands in horror and say, no, this sort of change is the equivalent of a world war. This is a huge change. It just looks small on a plot like this. So I think they're right about that. But I also think that they are possibly underestimating the sort of changes that we will see to global society and globally the economy, even at 2 degrees. I don't think we've really asked ourselves how climate change will impact the global economy, even at levels of sort of 2 degrees or so, which sound small, but are actually huge in terms of the history of the planet. Okay, I'm going to leave it there. My book details a whole series of challenges for climate change science and social science. I hope if you're interested in these things, maybe you'll go out to my book, or maybe you'll ask me questions about how these different types of challenges raise really interesting questions for how we go about academic study of climate change, as well as, of course, being tremendously important for how we respond to climate change as nations and as individual societies. But I'm going to leave it there because I hope that you will have questions. There are so many interesting things in climate change science and social science. Some of my papers are available at climateconfidence.net, and there are various podcasts out there on Apple and Spotify dealing with issues of my book. But I'll leave it there for the moment. Thanks very much.
All right, thank you so much, David. And we have a couple of questions. Thank you, everyone who attended this live. If you have further questions, please feel free to type them into the chat box. All right, David, for young people, what hope can you leave them with?
Yeah, so thank you for that question. And I since bringing out my book, I've been asked a question similar to that quite often, and I think it is hard to have hope. I think I struggle with this quite a lot. I think we are facing huge changes, and it is very, very worrying. But I think there are sources of hope, and essentially, I think when societies, when our nations, when our society changes, when we have new technology, when it decides to move in a different direction, history tells us that it can move very fast indeed. I don't think we're locked into our current ways of doing things, even though each year we get a new international meeting that sort of suggests that the changes are small. Nevertheless, I think when changes happen in our society, they can happen very, very quickly indeed. And I do see climate change getting real traction in societies across the globe. I don't think I don't think we're responding with sufficient seriousness yet, but it is starting to get traction, and I am optimistic that we can make changes very, very quickly. And that is also very much what I'm seeing in the expansion of renewable energy, uh, certainly in the UK, in Europe, but I don't have the figures for the US, so I apologize for that. But I believe in the US also the investment in renewable energy is massively progressing. It's still not enough, but I do think these changes can happen very quickly.
All right, very good. So speaking of renewable energy, for students who want to go into university and study climate change or environmental science, what advice would you give them, as in what high school classes should they take, or what interests should they do, or where should they volunteer? And maybe you could also speak about your background, because it doesn't seem like it wasn't a straightforward path to climate change.
No, it wasn't. So I have led a very peculiar academic path, and in all honesty, it hasn't been easy as an academic path. So I did physics at undergraduate level at university, uh, and I went on to do a master's in what was called energy systems and environmental management. I then spent 8 or 9 years working as a consultant, consultant on renewable energy projects before I returned to academia, did a bit of theoretical stuff, and then moved into climate modeling. So I did climate modeling, climate physics for a while, but that felt too distant from society. So I then kind of moved back. I wanted to do stuff that was related to adaptation planning and preparation, and that took me to economics and policy. So I now work across disciplines. I would say it's very hard to work across disciplines, and one of the whinges that I have in my book is that academia doesn't make it easy to bring disciplines together, and we really need to bring disciplines together. Hopefully, though, for those of you who are at high school or maybe soon to be undergraduates, by the time you get to the stage of really taking off in your first jobs, these things will have changed and will become easier. What subjects should you be doing? So I'm quite passionate about this. Actually, I'm a physicist. I love physics. I love nonlinear dynamics. I think there's wonderful things to do there. But it is not all about science and maths at all. It's about societies responding. For me, I don't think it matters. Do what most interests you. So it can be social science, it can be policy, it can be sociology. I think there's a really important role to play for psychology in terms of how we do the science, but also how populations change and how what they want, and how we can build societies that give them what they want. It can be in the arts. I've done work with artists, people working in theatre, people working in art installations. It's all about understanding the societies in which we live and how we can make them better. But physics and chemistry and biology and engineering are all important. It's what you're passionate in, do that, but then seek out how you can use your knowledge there to respond to climate change and to build our societies and our world to be a better place. There's so many opportunities out there, and we need to work across disciplines.
All right, very good. So, David, we're out of time. Thank you so much. And in the intro, I forgot to mention that your publisher was kind enough to donate 2 books, which are on my desk right now. And the lucky winners are Mary Starry and Mr. Al Tillman. So if you guys could send me your address privately right now, I will get them in the mailbox tomorrow. And once again, thank you everyone for attending this live. We have maybe 5 or 6 more webinars for this school year, and we encourage you to attend them. And thank you so much, David, for joining us for your evening, our afternoon.
Thank you so much.